All right, now we're going to study circular convolution. And unlike regular convolution, there's a parameter in circular convolution. We always have to specify n, which is the size of the circular convolution. Here I've written out the formula for circular convolution. It's similar in operation to the regular linear convolution that we're used to, where we have x of k, and then we have h of n minus k. But when we have finite length sequences that are each length n, the n minus k is evaluated modulo n. So one of the things to keep in mind here is that if the x sequence has length, we usually start by assuming that the x sequence has length n and the h sequence has length n. But if that's not the case, if x or h has length less than n, then what happens is we basically zero pad the sequence out to length n before applying these operations. So this looks a lot like linear convolution, but we have the modulo, which causes the circularity in the indexing. And the other thing that happens here is the limits of summation are always 0 to n minus 1. So we have this question. One, how can we make circular convolution perform like linear convolution? We'll study circular convolution in just a minute and look at some illustrations to understand what's going on and why is it not equal to linear convolution. And then we'll want to ask the question, how can I make circular convolution perform like linear convolution? Here's the formula for linear convolution, just to remind you. The summation limits in general are from minus infinity to infinity. And then the indexing here has no modulo as up above. It's just a time reversal and a shift. Then we multiply and accumulate to compute the convolution output. Here we do a circular time reversal and a shift by n samples, and then we do a multiply and accumulate to calculate the output. So they're similar in nature, but how can we make the circular perform linear? The next question would be, why would we want to do that? Well, the first answer is because the physical world performs linear convolution. And if we want to, in the computer, perform an operation that mimics the real world, then we need to make sure that it's a linear convolution. And the second part of this is, why would we want to? Well, speed is the answer, and we'll talk more about that in just a minute. So let's take a look at linear convolution and just review some of the ideas here. So if we have a sequence of length m and a sequence of length l, and we performed linear convolution, the result has length m plus l minus 1. And in the past we've talked about which of those samples are valid, which are transient, and so on. We'll ignore those questions for right now. With a circular convolution, if we have a sequence of length m, which is less than n, and a sequence of length l, which is also less than n, and we perform the circular convolution, the result will have length n. Also, it's not too early to remind you about the DFT relationship between circular convolution in the time domain and multiplication in the frequency domain. And this in fact is the relationship that allows us to do fast convolution by taking our sequences from the time domain into the frequency domain, multiplying them together, and then going back into the time domain. It turns out that in most cases that are useful, it's faster to go into the frequency domain and do multiplication rather than performing circular or linear convolution in the time domain. Okay, so let's jump into a Matlab example so that we can study this a little bit more and get an idea of what's happening. So in this example, I am convolving two sequences. The first sequence is a sequence of ones, and it looks like it's length 10. And then let's suppose that that's the x sequence. And then we also have this sequence that's indicated in orange here, let's suppose this is h. And in the linear convolution, what I'm showing you here is the steps involved in linear convolution. So we're leaving x alone, and we're taking h and we're doing a flip and a shift until the first sample of the impulse response h overlaps the input signal x. So you can see that product here. We're going to multiply those two values together, and that produces for us the output at time 0. Now down below, I'm also showing you the same input sequence x, it's length 10, and I'm showing you a circular time reversal of the impulse response. So in the linear case, the impulse response hangs off into the negative time index territory over here, but in circular convolution, we don't have that luxury. Those negative samples get wrapped back around and spill over here. So they actually overlap the other samples of the input signal. When we perform all these multiplications and add up all these results, we get a value that's equal to, about 3.5. And notice that that's different from the value 1.2 that we get from the linear convolution. Why did that happen? Why is it different? Well, the problem is that these samples over here wrap around. These samples in the negative domain, they wrap around and overlap the input signal. This happens because we're doing a 10-point circular convolution. Every time I hit the space bar, we step the impulse response forward one sample. So notice that in the linear convolution case, everything's shifted to the right by one sample. And in the circular convolution case, we got a right circular shift by one sample. Now in the linear convolution case, we multiply where there's overlap and add the values together, and we get an increase. And then down here in the circular convolution case, we multiply the values together, add them all up, and we get the same number we had before because the input signal is all ones, or 1.2. All right. Every time, watch what happens as I press the space bar and we advance the signal. You can see that at some point here, you can see that the linear time shift and the circular time shift at some point begin to be the same thing. Notice that at this point, you can't tell the two apart from one another. And so from this point forward, as we continue to do shifts, notice that from the output perspective, and also from the perspective of looking at the linear time reversal with the shift and the circular time reversal with the shift, these two things are indistinguishable. So if we continue to step this along, we'll see that the last few samples of this convolution, of the circular convolution, are equal to the last few samples of the linear convolution. And you can see why structurally that occurs in the pictures on the left. Now, but you can see that at the beginning, where we're getting a startup transient here in the linear, that didn't happen in the circular convolution. Now, I'm going to change things just a little bit. I'm going to run this again, but this time we're going to change the value of n, which affects the circular convolution, not the linear convolution. So remember, now we're going to do an n-point circular convolution, where n is equal to, it looks like, about 23 or 24. So again, at the top, we see the same picture as before. We see the input signal, and then we see the impulse response that's been time reversed and shifted so that the samples first begin to overlap. On the lower plot, we see a similar sort of thing happening. We see the circular time reversal of the impulse response and then the input signal. Notice that in this case, the circular time reversal of the impulse response looks okay, because the negative samples of the impulse response from the linear time reversal get wrapped around and they don't overlap the input signal. And so from the perspective of the output, notice that we're going to be okay. The circular time reversal, because these negative samples don't overlap the input signal, it doesn't matter whether they're located here or located on the negative time part of the axis. The point is that they multiply zeros, and so they contribute nothing to the accumulated value of the convolution. Now, as we tap the space bar and watch the circular convolution happen, notice that from the perspective of where the samples overlap, we're getting similar overlap patterns between the linear convolution and the circular convolution. It doesn't matter that we have this sample hanging out here on the negative side because it's multiplying by 0, just like it is over here in the circularly wrapped version. And so as we continue to step this along, notice that the circular convolution is producing the same output as the linear convolution. So once again, how did we make this happen? We made this happen by zero padding more than the minimum. What is the minimum amount of zero padding that's needed? Well, we can tell by going back and looking at the length of linear convolution and circular convolution. Remember that linear convolution is always going to produce something that's m plus l minus 1 in length. So if we let n, the number of points used in circular convolution, if we let n be greater than or equal to m plus l minus 1, then circular convolution is going to perform like linear convolution. Let's check this out in the example, the Matlab example. I'm going to go back and let n be equal to the very minimum, m plus l minus 1, and let's run this example again. So here we are. We've got the same things as before. We have linear convolution on the top, circular convolution on the bottom. And notice that in this case, where we went with n equal to the very minimum, that the negative time samples in the impulse response, when they wrap around in the modulo n case, they don't overlap the input signal. And as a result, as we step this through, the linear or the circular convolution will perform just like linear convolution. Now I want to go back and address the question about speed. Well, linear convolution, if we assume that m, the length of the input sequence, is much greater than the length of the impulse response, the number of multiplies and adds that you have to do to calculate the output of linear convolution is going to be about m times l, the product of the lengths. But if we exploit the DFT property, where circular convolution in the time domain is equal to multiplication in the frequency domain, we can take our sequences into the frequency domain using an endpoint DFT. And as long as there's sufficient zero padding, we'll be okay, as we've just explained. So if we take both of these into the DFT domain, multiply the DFTs together, and then inverse transform the result, we get the circular convolution of these two sequences. But if n is large enough, we know that circular convolution is equal to linear convolution. So this would be a fast way to perform convolution. And if we just calculate the numbers here, so circular convolution, again, if we assume that m is much bigger than l, we don't know why this is the case, but I've done a quick calculation to find that the number of multiplies and adds here is approximately equal to 3/2 times m plus 1, or times 1 plus the log base 2 of m. And if we just look at an example, suppose we have 1,000,000 samples and we want to run a filter on those where the filter has length 100. The linear convolution is going to take approximately 100 million samples, whereas if we do fast convolution, we only spend about 30 million samples. So that's a simple example, and the results can be even more dramatic than that. Let's do a quick example in Matlab. Let's suppose x is equal to 1 by 10, and h is equal to 1 by 5, or say 5. The convolution of x and h is this sequence that you see here. If we wanted to do this using the DFT, we could do this in a single line of code by doing the following. We could say inverse FFT of the FFT of x, and notice that the length of the output is 14 because that's 10 plus 5 minus 1. So let's do a 16-point transform. We'll zero pad a little bit. Then we'll multiply point for point times the 16-point transform of h, and let's look at the result that comes out. Okay, if we look at these values sample for sample, we have 1, 2, 3, 4, 5, 5, 5, 5, 5, 4, 3, 2, 1, and we get the same answers from this transform result. 1, 2, 3, 4, 5, 5, 5, 5, 5, 4, 3, 2, 1, and then we have 0, 0 at the end, because remember the convolution is length 14, and we've zero padded more than the minimum, and so the result that we get has some zeros at the end. So what's going on here is when we do, we can think of this built-in Matlab conv function as doing convolution the way we've learned about in the time domain, so we would consider that as being slow. When we use the DFT or the FFT, that would be considered fast convolution. And as you can see, you get the same answer whichever way you calculate it.